Hi folks, welcome to the first vectors lesson. So let's try to get an idea of what a vector is and why we need it. So I want us to remember our good old friend Broccoli Bear here. And Broccoli Bear in his lair could only move in one dimension. That is, he could only move in a straight line back and forth. All right, so if we were just interested in something like speed, like how fast Broccoli Bear was going, say 2 meters per second, okay, something like that does not need direction. Okay, it's just telling me how fast he's moving. But if we were interested in this idea of not just speed, but what we call velocity, in other words, where direction is specified, we needed to come up with a way of designating that. And what we did is we used the idea of a point of reference, say an origin, which we could call 0, and numbers on a number line to represent not only say how far Broccoli Bear is from the point of reference. So here Broccoli Bear is, say, 6 meters from the point of reference. At this point here, he's also 6 meters from the point of reference. But if we want to take that and talk about position, meaning not just how far from the point of reference, but in what direction, well, all we needed to do was use sign. So on this side here, position is positive 6. On this side here, position is negative 6. That extended to speed and velocity. Okay, moving at 2 meters per second, okay, just the speed, direction doesn't matter. Okay, whereas if the direction does matter, well, say it was 2 meters per second where the position is increasing at a rate of 2 meters per second, in other words, moving in the right direction, well, that was positive velocity. And if the position was decreasing, meaning moving towards the left, negative velocity. So we were able to describe direction just by using the idea of positive and negative. But if Broccoli Bear suddenly leaves his lair and is now able to move in 2 directions, in 2 dimensions, well, now positive and negative, we're going to see, is not enough to describe something for which we require a direction, because 2 meters per second in that direction is different than 2 meters per second in this direction or that direction. Okay, in fact, there's infinitely many directions Broccoli Bear could take, so positive and negative doesn't do the trick. So what we need is some new mathematical quantity that possesses both a numerical portion, okay, which we are going to call a scalar. Okay, so just say something like speed, how fast Broccoli Bear's going, so some positive number to represent the speed, and then something to represent the direction. All right, and well, a very typical way of doing that is using this idea of an arrow. Okay, why is this a good way to describe something which possesses both magnitude, okay, a scalar component, okay, and direction? Well, that's because the length of the arrow can represent the idea of magnitude, or that numerical component, and then the tip of the arrow can represent the direction. Okay, now this doesn't mean that because the arrow, say, is 4 centimeters long, that the magnitude is necessarily 4. You could have a scale for which each centimeter represents 4 meters per second, say. All right, so let's start taking a look at some of these notes here. So a scalar is a quantity which can be represented with just a number. So something for which direction either doesn't make sense, like salary, how much you make, you know, whether you're traveling in the east direction, west direction, doesn't make a difference, okay, or a quantity where we don't really care about the direction. So for example, if we're just talking about a distance that's traveled, okay, whether it's traveled in the east direction or west direction, if that's not of any importance to us, then that's described by a scalar, okay, just a number. As opposed to a vector, which is a quantity which is defined by both a number, which we call its magnitude, and a direction. So something like velocity, where we're interested in not just 2 meters per second, but in a particular direction. Something like force, okay, if somebody pushes Broccoli Bear coming from the left, he's going to move towards the right. But if somebody pushes him from the right, he's going to move to the left. So depending on what direction the force is applied, it produces a different motion. All right. Now, since we're defining a new mathematical object, we're going to need some notation. So here you notice that these notations, well, at least 3 of them, contain a little arrow on top. Not so surprising, since the arrow is our basic representation or pictorial representation of a vector. Okay, you'll notice this one here, though, is just a bolded letter. So in the old days, a little tough to get an arrow out of a letter. So if you just see a bolded letter, this represents a vector, as opposed to what we would have used in the past, which would have been a variable that's not bolded, which represents just numerical quantity or a scalar. Okay, and then we have here, what does this represent? Well, say this was point A and this was point B. So the vector would be the vector from A to B. And clearly, the vector BA would not be the same because it would be going in a different direction. Okay, so what is it that defines a vector? Its magnitude, or in this case here, the length of the arrow, and its direction, where the arrow is pointing. And this brings us to one of the most important qualities of a vector, is that it's movable. This vector, if I move it to this position, represents the exact same vector. Okay, so we'll talk about that in a second. All right, so here, let's give some names to the parts of this arrow here. So the start of the vector is what we call the tail, and the end of the vector, okay, is what's called the tip. And this is where we see that as we go from tail to tip, it designates the direction of the vector. Okay, now very often we're going to be dealing with scenarios where there's more than 2 vectors involved. So let's say there's some force on our object coming from 2 different directions. We're going to need 2 different vectors. And so we want to be able to describe them with respect to each other. So we talk about the angle between the vectors. So there's 2 reasonable places, I would say, to place this second vector, either here or there. Okay, in this case here, I guess this angle, if we place them tip to tail, this would represent the angle between the vectors, or the other reasonable option is to place it tail to tail. And this is what was chosen as the convention. So anytime they talk about the angle between 2 vectors, it is assumed that these 2 vectors are tail to tail. Now, we're going to see later on that sometimes you might want to move one of them. That's fine. But the angle that's represented is this angle here when they're placed tail to tail. All right? So let's talk a bit more about working with more than 1 vector. So here, what does it mean for 2 vectors to be equal? Well, what did we say? We said that a vector is defined by its magnitude and its direction. So if I have a vector with a particular magnitude, length of the arrow, and a particular direction, where the arrow is pointing, and I have another vector with the exact same length, pointing in the exact same direction, these 2 vectors are equal, regardless of the fact that they're in different positions. All right? What does it mean to be opposite? Well, it makes sense that we might be interested in 2 vectors that have the same magnitude, but pointing in the opposite direction. Okay? Think of if Broccoli Bear's standing on the floor. Okay, Broccoli Bear's applying a force due to gravity downwards, but then the floor is applying a force equal and opposite to Broccoli Bear upwards. Okay, so we need a way to describe these opposite vectors. Okay, so same magnitude, just opposite directions. And then we talk about parallel vectors. Now, it would make sense to define parallel vectors as just 2 vectors that are pointing in the same direction, regardless of whether they have the same magnitude or not. But we actually extend that definition a little bit because we also include vectors that are in the opposite direction. So vectors are parallel if they are in the same or opposite direction. So this is where you realize that equal vectors are parallel, opposite vectors are parallel. Okay? But you also have scenarios where their magnitudes might not necessarily be the same. All right? So we have an arrow representing the vector going from tail to tip. All right. Now, this is a very nice, and I used the word pictorial before, it's a very nice way of representing this idea of a vector visually. But unless you're going to only be working with rulers and perhaps protractors to solve problems, this is not a very algebraic, no, it's not a very numerical way of representing vectors. So we'd like something that defines vectors in a more numerical way. And this is where we have an alternate description of a vector, where we give an explicit magnitude. So in this case here, if it's a velocity vector, so 25 kilometers per hour, and then we specify a direction using the cardinal points, north, south, east, west. Okay, so here we got north, south, east, west. So what would this represent? Well, a vector that starts towards the north and then moves 30 degrees towards the east, north, south, east, west. So our vector would look something like this if we were representing it using cardinal points. So the length of the vector would represent the magnitude of 25, and then here we have in the north direction 30 degrees towards the east. Okay, so this is going to be one way in which we're going to represent vectors that's going to allow us to do some calculations. Okay, but you notice here I say others to come because there's going to be a much more important and much more useful way of defining vectors that's going to come along later on. All right, so if I'm interested in specifying the magnitude of the vector, well, I need a notation. All right, so here the magnitude of a vector is denoted, well, these two bars. Now you'll notice that looks a lot like absolute value. Now when you think about it, it's not surprising they would use that, because if we're talking about, remember in one dimension we were just using numbers. Well, if I'm at position 4 or position -4 and I'm just interested in the distance away, well, I could use absolute value to represent the distance from the origin. So not surprisingly, they chose the same symbol to represent magnitude. So if you see a vector inside, these two bars represent magnitude. If you see a number inside, it represents absolute value. All right? So we talked about this idea of the angle between two vectors has them placed tail to tail. Now, very important that it's the angle that's between 0 and 180. It's not this angle on the other side, which is larger than 180. So it's assumed to be the smaller of the two angles. All right? So we talked about two vectors being equal if their magnitude and directions are the same, and they're opposite if their magnitudes are the same, but they point in opposite directions. Now, not surprisingly, again, going back to this idea of our work in one dimension, okay, if I'm at position 4 as opposed to position -4, hey, why not co-opt the negative notation to represent opposite? Okay, so when u and v are opposite vectors, we can say that u is equal to -v. All right, and we talked about two vectors being parallel if they possess the same or opposite directions. All right, so now we're going to go to our first operation with these new mathematical objects, because if we're going to be dealing possibly with more than one vector, we need to find ways of combining them. In other words, operating on these vectors. All right, and let's start with this example here. If I have some vector u, and I want to create a vector that's in the exact same direction as vector u, but 3 times longer. Okay, well, I can think of it as taking my vector u, putting another vector u, and then a third vector u, one after the other, and what have I created? Well, I've created a vector that's in the same direction, but 3 times longer. All right, so essentially, I'm not changing the direction. The only thing I'm changing is that numerical component, okay, the magnitude. So it makes sense that I would use good old multiplication. Okay, now I want you to look here. The u is bolded, representing a vector, and this here is just representing what we call a scalar multiple. In other words, multiplying a vector by a scalar. What does this represent? It represents the vector that's in the same direction as u, but 3 times longer. So I've taken the magnitude of u and multiplied it by 3. All right? So if I want, say, a vector that's 2 times longer, but pointing in the opposite direction, well, again, if I want to take this vector u and make it twice as long, I'm going to multiply it by the scalar 2. And then we remember that opposite vectors are represented by a negative. So the way we represent this vector that's twice as long as u, but in the opposite direction, not surprisingly, is going to be negative 2u. All right? So let's talk a little more about this scalar multiplication. Okay? So if I have my vector u, all right, and I want the vector that's 3 times longer, okay, 3u. Okay, but in the same direction. Well, if I want to look at the magnitude of my new vector, well, I see that it's just 3 times the magnitude of my original vector. Okay, so very nice, simple, makes sense. What I want, it's this new vector, what we call a scalar multiple of my original vector. Okay, the magnitude of that new vector, in this case, it would be just 3 times the magnitude of the other vector. All right, need to be a little careful though, because if I'm taking again my vector u, and I want something that's twice as long, but in the opposite direction, well, if I'm calling this negative 2u, and I want to take the magnitude of that vector, well, it doesn't make sense to write negative 2, this scalar multiple, times the magnitude of u. Because remember, the magnitude just represents the length of the arrow. It's supposed to be a positive number. So what's an easy way to take care of this is instead of just using this scalar multiple in my magnitude formula, I just take the absolute value. Okay? Now, if the number is already positive, doesn't make a difference. But of course, if the scalar multiple is negative, it will just turn into some positive number, which is exactly what I want. All right? So the way in which we define that is we define this idea of scalar multiplication. In other words, multiplying a vector by a scalar quantity. For now, we'll keep k not equal to 0. You can sort of see that k equals 0 is going to bring some challenges. We'll talk about that later on. But what it does is it gives me a new vector which is parallel to the original vector, meaning same direction or opposite direction. All right. And the magnitude of the new vector is just given by the absolute value of k times the magnitude of the original vector v. All right? So again, notice here we have to understand the difference in this notation. In this scenario here, k is a scalar, hence the 2 bars represents absolute value, and then here v is a vector, so the 2 bars represent magnitude. All right, so the last thing we're going to look at here, okay, which is a nice application of scalar multiplication, is if I have some vector v, all right, and say this vector v has a magnitude of 6, I might want to create a vector that's in the same direction as v, but has a magnitude of 1. All right. Now we're going to see as we go throughout the through the course that this is going to be a useful thing for us to do. Okay, to be able to easily create a vector that's in the same direction as a given vector, in this case v, but that has a magnitude 1. In fact, this is so important that we give it its own symbol. We call this v hat. Okay, so this represents a vector in the same direction as v, but with magnitude 1. But we already have an operation that takes a vector, gives us a new vector in the same direction, but changes only its magnitude. That's just scalar multiplication. So you got to say, if the magnitude of vector v is 6, how am I going to create a vector that has a magnitude of 1? Well, if I just multiply 6 by 1 over 6, okay, well, makes sense that I would be multiplying my vector v by 1 over 6, okay? Because what's this going to create? It's going to create some vector that is 1/6 as long as the original magnitude, all right? So if we want to see this in a little bit more of a general context, okay, if I have some vector v and I want to create some vector which is in the same direction as v, okay, but has magnitude of 1, well, what I want to do is I want to take vector v and multiply it by some scalar multiple. Okay, so the question is, what's k going to be equal to? Well, let's apply our definition for the magnitude. So this is just going to be the absolute value of k times the magnitude of v, and this needs to be equal to 1, and so k is just going to be 1 over the magnitude of v. All right, and since the magnitude of v is positive, this is in fact already going to be a positive number. All right, so what is my k going to be? Just 1 over the magnitude. So what's going to be my unit vector in the same direction as v? 1 over magnitude of v times v. Okay, or we allow ourselves to use the idea of division, okay, and think of it as the vector v divided by its magnitude. So if the magnitude is 6, I just divide the vector by 6. If the magnitude is 10, I just divide the magnitude of 10 by 10, and this gives us this result, that if I want to create a unit vector in the same direction as v, I just take v and divide it by its magnitude. And that's it for this first lesson.